I will be talking about classical partition functions and how we can look at some algebraic structure in a quantum framework. I would like to, this is, let's say, it's the structure of the talk. So just giving some motivation for why we're doing this, the basic idea of what we would like to understand, and then some results on what we did understand and some possible implementations of the, say, the algebraic quantum structure that we found on quantum computers. Okay, so our motivation and context for our work comes from let's say, hard classical problems, the standard class of which is probably binary optimization, and it has been very much studied in the last few years since it's a hard problem, of course, and it has very nice implementations, I mean, very natural implementations of quantum computers. For many decades, there have been developed a lot of tools for solving these problems, and they can tackle very large system sizes with some guarantees or no, some heuristics. So, for instance, if you read some of the more recent papers, the largest sizes that one is typically able to handle is something like 10,000 vertices on certain classes of sparse graphs. And in the last few years, also, some quantum approaches have been developed to tackle this problem. Of course, possibly the most natural one in which this optimization implemented is quantum annealing, but also variational quantum algorithms and many more related algorithms. So I will not be listing them all, but just to say that this is an interesting problem and a hard problem. The typical way in which this is tackled is simply taking the original formulation in terms of some bit strings and a cost function, which we want to minimize or maximize. And then we simply translate this to the quantum realm by mapping the bit strings to a computational basis, and therefore working no longer in a discrete space, but in a exponentially sized Hilbert space. And so we want to minimize the energy of a certain Hamiltonian that we have assigned. And here we'll already see that for modern implementations, we are very far from reaching what sizes that can be tackled by classical computers. Namely, some of the largest quantum computers that we have now can reach only up to hundreds or, in some rare cases, thousands of qubits. So we have a problem of limited memory and also circuit depth, because these are noisy devices, and so we would like, as much as possible, to reduce the circuit depth of our circuit running the algorithm. We decided to look at a different way. Decided to look at this problem from a different angle, which is by looking at the generalization given by finite temperature Ising models. So now we have a statistical description, and these are still hard at finite temperature in general. So we have not simply by turning on the temperature, we have not made the problem trivial. And again, also for finite temperatures, many classical approaches exist. Probably the most used one are Monte Carlo methods, but also more recently tensor networks, and even in certain cases, dedicated hardware solvers. One of our questions in tackling this problem was how can we take advantage of the algebraic structure of the problem, or maybe restricting ourselves to a certain class. And to show how this comes out, we go back to one of the simplest Ising models that exist, the 2D Ising model. This is a model on a rectangular lattice where we have nearest neighbor interactions, and we assume here that we have some uniform interactions between rows and between columns. We have, therefore, an equilibrium description because we're interested at finite temperature. So to each configuration, we assign some Boltzmann weight depending on the energy. And one of the first quantities which comes up that we would like to understand is the partition function, which serves as normalization of our Boltzmann weights. We can also see immediately a connection to the optimization problem, because if we turn the beta to plus infinity, then the only configurations which survive are those with the lowest energy, meaning that the only relevant configurations are the ground state configurations, so connecting to the optimization version. More generally, the quantities that we would like to understand are maybe some free energy, their derivatives, specific heat, as well as correlation functions. And in all of these, we see that the partition function is, let's say, a central quantity that we would like to compute. And naively, we run immediately into a problem, which is we have an exponential number of configurations, since each spin can take on a value 0, 1, plus or minus 1 independently. And so we are stuck with a naive algorithm which runs in exponential time. One thing we can do to improve upon this runtime is by realizing that the connections between two rows, which actually I think here are columns. No, here there are rows. Only 2 rows at a time appear inside the Boltzmann weights. And so we can factorize the probability and define a certain matrix of weights, which we call the transfer matrix. This is, of course, a very, very, very old mapping. And what comes out after some simple algebraic manipulation is that you can write the partition function as a trace of this matrix of weights. Not only that, but also this matrix turns out to have a very simple expression. So it's just a product of exponentials of something which is diagonal in the computational basis and something which is off diagonal and relates to the interactions between 2 rows. So now, instead of having a 2D classical model, we have a 1D model where we have ZZ interactions related to interactions inside the classical row, and then on-site interactions related to on-site terms related to interactions between 2 different rows. With this formalism, of course, we can compute potentially any thermodynamic quantity, namely the correlation functions, which just require including also some z's inside the trace of this product. And we see here that this is let's say an imaginary time evolution, because here we have no i's, and of log k kind, because we have imposed that between 2 different rows, the interaction constants stay the same. So we have reduced the complexity of the problem in a sense, because now we have a very compact representation instead, where we have an m qubits representing n by n spins. Of course, now we are stuck again with computing something which is potentially exponential, because we have to compute the trace of this matrix V, which lives on a 2 to the n dimensional Hilbert space. Since we have translation symmetry, in the end, what we end up caring about is just the maximal eigenvalue, because everything else only contributes to exponentially small corrections. And the reason why we are able to solve this model is that it turns out that these transfer matrices, so these products of exponentials here, actually come from the representation of a very small group, which is essentially, in physical terms, is very well known from the Jordan-Wigner and free fermions transformation. And the reason why we can solve this model efficiently is that essentially we have to deal only with polynomially sized matrices. So we have some matrix of size linear in the size of the quantum system, and then in polynomial time we can find its eigenvalues, and from there we can map it to the original transfer matrix by considering specifically the maximal eigenvalue, although through a very simple formula we are able to potentially compute all of them. And indeed, one is able to go beyond just this maximal eigenvalue case, but with the exact formulas compute the whole trace. Okay, so we have a very nice solution, because we started with something exponential, but we are able to reduce it to something only polynomial. So one of our questions was, can we do something like this? More generally means not every Ising model, but we consider a restricted class of Ising models. So again, we want to keep the layered structure of the model, because we want to group together spins which will define our quantum system. So here we take some arbitrary connections inside a layer, and then some connections between adjacent sites. So only specific connections between corresponding sites in a layer and the next. And we allow for generality connections, so interactions, as I said here, but also on-site magnetic fields. So again, we can define this transfer matrix relating now a layer and the next. And from the point of view of the quantum system, we have additional terms. So not only interactions between qubits, but also two types of on-site interactions related to the magnetic field and the connections between 2 different layers. And in terms of this, we can compute the partition function and the correlation functions. So in the case of m by n, let's say, layered grids, we get a reduction to only m qubits. I will also point out here that in the case where we don't choose periodic boundary conditions, but only open boundary conditions, that we no longer care about the trace, but only a specific matrix element, which will come up later. So we have a restricted class of models, but can we tackle actually interesting models with this class, with these types of interactions? And the answer is yes. We can tackle NP-hard problems from NP from the optimization point of view, where even if in the 2D connectivity we include just magnetic fields, we are jumping complexity from polynomial to potentially exponential. And similarly, even if we don't have magnetic fields, if we increase the dimensionality, and so the connectivity, by going to a 3D lattice, we're also increasing the complexity of the problem. So the question is, given these kinds of results, what happens to the representation of the group of the transfer matrices? And also, maybe not for all cases we can find something which is efficient, but can we find maybe some special cases for given connectivities where this becomes easy? And this is what I will be talking about now, although I will mention, I hope you did not get too tired of all the Lie algebra talks, because now I will mention some background. Why do we care about Lie groups and Lie algebras? The reason is that when we are dealing with this type of imaginary time circuit, this kind of object lives inside a real Lie group within the whole group of invertible matrices. And we can understand a lot about this group just by looking at infinitesimal generators. So we don't need a whole complicated topological understanding of the group, but just we look at more simpler linear object where we have some, because the Lie algebra corresponding to this Lie group is essentially a vector space plus an operation. So mathematically a much nicer object to look at. And from the Lie algebra, we can already understand most things, if not everything, depending on exactly which Lie group we have. Specifically, its dimension, invariant subspaces, so how it acts on the Hilbert space, and so on. But the main question that we want to ask is really, okay, before we had a very small Hilbert space, and so we were able to solve the problem by going, we had a very small Lie group, thus Lie algebra, and so we were able to solve this problem by going to the standard representation of this Lie group and solving it there. So can we do this also for general Lie groups of polynomial size? When do we get something polynomial, and when do we get something exponential? So now our task is computing the dimension of this Lie algebra. We are given some generators, and we want to try and understand what we end up with. The first approach that we can try is just brute force. So we compute nested commutators, we check for linear independence, but then we end up with something which is not scalable, and also some only finite n. So it does not tell us about the scaling for any n. The next approach one might try is just induction proofs. So we try to come up with some solution for a given n, and then from there understand what happens for larger sizes. But this is very difficult because it depends exactly on the generators you're given, and also here we have an additional dependence on the graph. We don't have just one size, but really we would need to understand what happens for general connectivity. Apart from this, we can also have some specific techniques. So there was also one of the posters here dedicated specifically to understanding Lie algebra with polys. But really, we don't use any of this. We kind of cheat in the sense that we essentially already know the answer from the literature, specifically from Robert's work, which you also might have seen in the presentation the first day. Because this looks, so the generators we're given look very much similar, where there's only an I missing. So really, okay, we know the answer. But in principle, it is not so easy to see what is the connection. The simplest thing that we can see is, however, that if we relax the constraint where we are only taking real linear combinations from linear to complex, then we see that immediately both, if we exclude here the local magnetic fields, both generators give rise to the same complex Lie algebra. So at the very least, we are able to bound the dimension of this normal Lie algebra by twice the dimension of the compact version, so the one which appears in the QAOA setting. But we can do better than that, and that's what I'll try to go over now. Okay, so we saw that essentially there is just an eye missing. So what we would like to do is have a procedure where we just turn on and turn off an eye and understand precisely what the Lie algebra is given the starting one. In general, this is not so trivial when we consider the non-abelian setting. So we don't have just one interaction Hamiltonian, but possibly multiple ones. And the simplest example that we can consider is one where we have an SU2, so two generators IX and IZ, and it is spanned by three elements. So one might think, okay, let's turn everything from I's, let's put an additional I on top of everything, which means we transform each an IX to X, IZ to Z, IY to Y. And so we have this kind of correspondence where we have some real-time evolution in terms of unitaries, and then some imaginary time evolution in terms of the corresponding polyoperators. But if what happens if we do this is that we get something, we get essentially a double copy of the original system, because through commutators, say X and Y, we get an IZ, and so from the commutators of the purely Hermitian polymatrices, we also get the skew Hermitian ones. So what we end up getting is the full complex Lie algebra. So in the previous slide, this would mean that essentially the Lie algebra that we get saturates this bound. But this is not what we like to do, because we know that the Lie algebra that we have has actually a real structure. The transformation that we actually want to use is something like this, where we only look at certain generators, and then we turn off the eye. And from here, we get some, say, only partial change from real time to imaginary time, because actually we are keeping the I in front of the Y, because the commutator of X and Z is IY, so we only get three elements, as in the original SU2, and this is in fact, say, the kind of transformation that we want to look at, because we expect that by going from real time to imaginary time, we keep the real structure and specifically also the dimension. As another example, I will just mention, here we see that essentially only two possibilities are allowed if we care for real Lie algebras starting from a complex structure, but in principle there can be many different choices. So we can just imagine we have some bases, we turn on some eyes in some of them, and then we get different Lie algebras at the end. So for instance, if we start from the orthogonal Lie algebra of dimension 4, we can have two choices, which lead either to something of to rotations of different signature. So here plus 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 minus, and here plus plus minus minus in the metric of our rotations. Okay, so we need a different language, a precise language to understand these kind of rotations, and this is offered by looking at certain involutions in our starting Lie algebra. Looking at these involutions, we see that there exist two invariant subspaces, one corresponding to the +1 eigenspace and one corresponding to the -1 eigenspace. Now we can in fact turn on an I in a meaningful way, in the sense that by just adding the I to the minus eigenspace, the resulting Lie algebra is well defined. So we do not get any additional generators, unlike here where we were turning on the I in all of the basis elements, and we were getting something of larger dimension. So really, through going this procedure, dimension is conserved. Of course, dimension is not the only thing that we care about, but we would also like to understand precisely what is the Lie algebra that we get. It's in principle not trivial, because as I mentioned, there are multiple choices that one can make of rotation from real time to, let's say, partially imaginary time. However, we are in luck in the sense that there are two special cases which are in fact the ones of interest to us. The compact one, which corresponds to real time, and corresponds also to the fact that any element in the Lie algebra can be diagonalized with purely imaginary eigenvalues, and also the maximally non-compact one, or the split Lie algebra. Diagonalization is not possible for all elements, but it is possible for those contained inside let's say, the special -1 eigenspace of the involution. And here also we get purely real eigenvalues. So this is really the object that we would like to have, because we are starting from a real context, the one of partition functions, classical partition functions. So what do we get? I will not go into details of the proof since I hope I did not bore you too much with the details. But what we end up finding is that the thermal Lie algebra, which comes up in these layers of a classical Ising model, is precisely the split real form corresponding to our compact Lie algebra in the quantum setting. And from this, we can immediately deduce what the Lie algebra is in our case. So one of the results in Robert's paper is that for the cycle graph, the free ansatz on the cycle graph is 2 copies of the orthogonal Lie algebra. And from there, we go to the split version, which simply corresponds to orthogonal rotation with the equal plus and minus signature. Whereas in the bipartite case, we get something exponential, specifically the unitary symplectic Lie algebra, and in the thermal counterpart, we get the real symplectic Lie algebra. So specifically, we find exactly what we expected before, where in the 2D case, we get something exponential, and in 3D, we get something exponential, so which matches our expectation from the hardness of the problem. But this means that, in some sense, it is bad news, because the only thing that survives in polynomial size is essentially just the 2D Ising model. So really, we are stuck just with which corresponds to taking a layer of our classical model to be either a line or a circle. And in all other cases, we get something exponential. So we cannot hope to apply the method as before. And if we apply also magnetic fields, we get something even worse, where even when the graph is a line or a circle, so corresponding to the Ising model, we always get something exponential. So the answer to can we get some efficient computation maybe by changing the connectivities is no, unfortunately. Still, something that we wanted to understand is, can we implement this on a quantum computer and possibly try to take advantage of the algebraic structure of the problem. So we go to the second and final part of the talk. How can we implement this on a quantum computer? Well, of course, as I've mentioned multiple times, the transfer matrix that we're looking at is not unitary. So we cannot just implement a series of unitary gates on a quantum computer and from there compute thermal quantities. So we need some way to implement non-unitarity. And by looking at the literature, we consider 2 possible approaches. One is essentially by introducing non-unitarity via measurements, and the other is by using approximation with unitaries through a classical counterpart. I will consider first the first approach. Okay, so what happens in this case? What one can do here is, okay, we want to implement the action of a certain non-unitary operator onto a vector. What one can do is encode this inside a larger unitary. So in such a way that given a certain ancilla which interacts with our system, the resulting state is the matrix which we want to apply, suitably normalized, plus something else where the ancilla is in the one state, which we can project out by doing a measurement. So how do we, given a certain D, how can we realize, at least in principle, this block encoding? The intuition is actually quite simple and comes out simply from Euler's identity. We have some real angle theta, and some real value cosine of theta that we would like to apply to our vector, and simply the exponential with angle theta of the x gate that gives us something which is purely real on the diagonals and purely imaginary on the off-diagonal terms. So with the only constraint that now we have to keep our diagonal terms between -1 and 1. Hence why we need this normalization constant here coming from unitarity. So in general, what one can do, given, say, Hermitian operator, which we can diagonalize, is block encode this in the eigenbasis of the system. So now instead of giving a singular angle here, we give a series of angles corresponding to the diagonal terms of our matrix that we want to implement. Again, with the constraint of that the resulting values are between -1 and 1, and so here we need some normalization constant which bounds from above the eigenvalues of our matrix. This can also be generalized to non-diagonalizable matrices, simply with the SVT transformation, where we can go to something diagonal by applying on both sides some two different unitaries. And the two unitaries essentially do not interfere in this process because being unitary, we do not need to block encode them. So we just act on the physical system with this unitary U and V, and then the resulting unitary encodes precisely our diagonalizable matrix M. Of course, this approach, while intuitive, is quite naive because we have some problems. Namely, okay, we are given RD, but how do we compute our matrix theta of angles which determines our block encoding circuit? Because first we will need to potentially diagonalize this matrix and also store all of the exponentially many values. And if we could do that, we would probably not use a quantum computers in the first place. And also, even if we do have a nice representation of theta, in principle, this could be exponentially long because this theta does not play nicely with the eigenvalues of D, and so we could end up having, say, if D is diagonal in the Z basis, then this could be an exponentially long sum of Z terms. So what we do is take advantage of the structure of the problem, at least in a minimal way, in the sense that the imaginary time circuit that we're given is something we can compose in local gates. What we can do is consider a block encoding of just Pauli matrices, or rather exponential of Pauli matrices. And this turns out to be quite simple because the only gates that we need to implement are one single qubit rotations on our ancillas and two some rotation around an enlarged Pauli. So the P is the original Pauli that implements the imaginary time rotation, and then XA is the X gate corresponding to the ancilla gate. If we have two possible approaches that we have considered, one consists in adding an ancilla for each gate and then measuring only at the end. And the other, which allows for more variable number of ancillas, is to perform measurement for mid-circuit measurements, so that in principle we can reduce the number of ancillas up to 1 by just executing a circuit in a sequence. Of course, the problems here it's more obvious. In principle, we will need exponentially many samples in order to run our circuit with success. What ends up happening is if we do not get a result 0, in this special case, we get an imaginary time evolution in the opposite direction. So instead of e to the tau p, we get something like e to the minus tau p. Here, it's not immediately obvious what happens, but I will mention it later when we go to, concrete implementation of this for computation of quantities. Since until now, I'm just looking at what happens to implement our transfer matrices, but that's not what we want to look at. We want to compute thermal quantities such as the partition function and correlation functions. Okay, so now we look at what happens, what one can do with purely unitary operations. And here, essentially, the main observation is that up to normalization, any non-unitary matrix acting on a vector returns a normalized vector, and therefore there is always a certain unitary which can bring us from the starting vector to the final vector. So the task is really finding this unitary here. How can we do this? Well, there have been a few approaches that have been developed, but essentially what one can do is, say, specifically in the case of imaginary time evolution, so we have some imaginary time exponential parameterized by our time tau, with respect to which we also parameterize our unitary operation. And the idea here, one of the idea here for variational imaginary time evolution, which was proposed a few years back, is essentially to first translate our problem of imaginary time evolution into a variational equation. And from there, instead of considering variations over all overall possible states, we consider only a restricted manifold, which is given by our parameterized unitary circuit. And in order to solve this problem, we then go into a feedback loop, because in order to update our parameters iteratively, so we start from the initial state, and then we want to find out how to go to the next one. We need to perform some measurements, many measurements on top of the circuit to understand what is the law which governs the equation of motion of our parameters. So now that we have these implementations, how can we actually compute things? And in principle, this is very easy. With the only thing that we need to do is, since we are only interested in computing traces with respect to an initial state of our matrix, where the initial state is now, we can consider, for instance, periodic boundary conditions, the maximally mixed state, and for open boundary conditions, also the plus state, so instead a pure state. And in the case where we perform, let's say, in this case here, so we don't perform mid-circuit measurements, and we're using unitary block encodings, the only thing that we need to do is just perform our Hadamard test on our encoding unitary operator, since by initializing the ancillas into the zero state, what comes out of the trace of this unitary operator is precisely the quantity that we want to look at. So specifically, if we encode the partition function as a product of all our transfer matrices, that what we end up getting from this circuit is precisely the trace, is precisely the partition function up to normalization constant. Also, this requires very simple implementation, because the only quantity that we look at are just expectation values on top of an additional control qubit. Similarly, we can do this also for correlation functions. So now we add also z-gates in between products of our transfer matrices, which also does not change the normalization of our block encoding, since these are unitary matrices. And so what ends up happening is that we simply have a very simple relation between the correlation functions as a ratio of traces, which can be rewritten as fractions of observables in our two circuits. And here I would also mention, what are the challenges with this kind of implementation? Here we can see it more clearly. It really comes down to the kind of approximation that we can get. Because if we want to estimate something which is exponential in size, then if what we get on the other side is also exponential, then to achieve a good multiplicative approximation ratio, then in the general case, we will have to do exponentially many measurements. So of course, in general, this approach does not avoid the exponential overhead in the computation of the partition function. And similarly for the correlation functions, although here it is not as clear whether this kind of argument applies, and actually something we're still trying to understand. In the other case, so where we perform bit circuit measurements, we do not need to keep all of our ancillas, but we are stuck with the requirement of potentially performing many repetitions per circuit. But again, in order to compute the partition function and observables, we simply need to simply execute the Hadamard test with respect to this non-unitary circuit, and this time it really is non-unitary because we have performed measurements inside of the circuit, which also justifies the presence of these additional terms, which comes out of the fact that when this non-unitary operator acts on the control qubits, we are throwing away parts of the wave function, because we would not expect that just the control is able to affect the magnetization of our control qubit. And finally, I will also mention what happens in the variational case, where we are constrained to only considering open boundary conditions, because we can treat this with the variational approach, we can only consider pure initial states. And the circuit that we need to consider is no longer just a controlled version of our encoding unitary, but really we need to have a unitary which mimics the whole controlled non-unitary circuit. Okay, so we come to the end of the talk, and what we have seen is, let's say, two parts. One was focused more on understanding what happens for general models, what does the transfer matrix look like, and if we can have some, first of all, some nice characterization of the Lie algebras, which we can have, but unfortunately we cannot use this for other kinds of polynomial time efficient solutions beyond the 2D SE model. And we also consider possible implementations, quantum computers, by taking advantage of the local structure of the imaginary time circuit, although it is really an open question whether we can in fact take advantage of the algebraic structure also in the quantum setting, because until now we have only used, say, the decomposition of the imaginary time circuit into local gates, but we have not used the specific Lie algebra that we get. So it is until now an open question how to make best use of this. And some other questions that we would like to understand also relate to more general interlayer interactions, because we really have some very strong constraints on the possible connectivities between two layers. And one of the first questions is, do we still get, for general parameters, something invertible? An intuition would say yes, because a random matrix will have non-zero eigenvalues, and so will be invertible. But since we are dealing with structured problems, this may not necessarily be the case for certain specific classes of problems. And also, even if we do have invertibility, one of the main properties we want to understand is, okay, do we still have locality? So do we have some nice decomposition into some specific set of gates, which may be either, let's say, some polys or some sum of polys, potentially. Another question is relating to what happens to the more general case. Specifically, if we had symmetries, there are examples where the dimension of the Lie algebra is polynomial, but it is not still clear whether for under this general hypothesis we can still get some polynomial time algorithm, either classical or quantum, for the computation of the partition function and thermal observables. And finally, as you can see, it really is about proposals of quantum algorithms, but we would like to understand first theoretically, but also practically, how this algorithm performs, and so what are the precise approximation scale regimes depending potentially on parameters and connectivities. And also if we can come up with some better block encodings which reduce the number of ancillas, and so make it potentially implementable on current quantum hardware.